Hello everyone, I'm Andrea Vezzosi, and I will present our article about partial univalence in an n-truncated type theory, which is joint work with Christian Sattler. So it is well known that uniqueness of identity proofs is incompatible with univalence. The simplest counterexample is that we can build two equivalences between bool and itself, given by the identity function and by negation. And these act differently when turned into a path by univalence, and then used to transport elements of bool. The first one will just send true to true, and negation, of course, will send true to false. But if uniqueness of identity proof is true, then the two equalities should be equal themselves. So they should act the same when used to transport an element of bool. And this will lead to a contradiction. However, there are a bunch of developments, right? Everything that is worried mostly about formalizing or encoding what can be called set-level mathematics, where UIP will be a very convenient assumption. One, because, well, everything that morally is a set should satisfy uniqueness of identity proof anyway, because when we think of sets, we think of objects that don't really have an interesting equality, right? In standard set theories, equalities are just a property. They don't have any structure. And of course, if you can assume UIP, then proofs about paths become trivial. And one example of this is that the notion of equivalence kind of reduces to the simpler notion of isomorphism. So somehow UIP would be appealing to have for this kind of developments. And if we think about what homotopy type theory is without univalence, we still have features that are very interesting and that kind of are very useful to have on top of a more standard Martin-Löf type theory. First of all, we have function extensionality, but also higher inductive types that allow one to essentially introduce quotients. So propositional truncation, constructing initial algebras for theories defined by both term formers and equations. Other form of quotients like colimits in a category of sets. But the problem is that without univalence, some proofs we would like to have about these higher inductive types actually are not available, right? Are not possible to be proven. In particular, it's quite useful to be able to at least have proposition extensionality. So this restricted form of univalence where you can prove that two propositions are equal whenever they are logically equivalent. And by proposition, I mean types for which any two elements, like is defined for E5.A here, types for which any two elements, x and y, we can prove that they are equal. So for example, membership in finite sets will be a proposition, and it can be defined kind of by recursion on the syntax of finite sets, right? We can give a grammar of finite sets that, for example, includes the union operator, but then when we try to define membership on it, we need to prove that this membership operator respects commutativity. And so we need to prove this equality, that A member of X union Y is equal to a member of Y union X. And of course, these are not they're not provably equal without something like proposition extensionality. Another general property that's very useful is that being able to prove the effectiveness of quotients, which means that whenever you have an equality between two elements of the quotient given by the inclusion of an element of A into the quotient, well, these are equal if and only if they are related by the relation we quotient by. So indeed, even if you're working just with sets, it is quite desirable to have at least univalence for propositions, because it enables these kinds of proofs. And note that here we are talking about propositions as definable internally. As I said, the ones that for which any two objects we can prove they're equal, and not propositions as, for example, members of a prop universe, like one could have in the meta theory of, for example, Koch. We believe this makes it for a simpler theory, but it is somehow more challenging to model, and that's why our consistency proof will be, as we will see in a short while. So, what's the result of this paper? We will prove that this form of partial univalence, so univalence for a restricted class of types, is actually consistent with with an assumption of truncatedness, right? So zero truncatedness corresponds to UIP, and univalence restricted to n-1 types corresponds to the univalence for propositions. So what we will do is we will build a model of a type theory with the standard type formers like pi, sigma, natural numbers, and W types in general, and a hierarchy of universes. And this type theory will also model higher inductive types, but truncated to a certain level n, because in general we will have truncatedness to n for every type, and univalence will be restricted to n-1 types. How will this model look? Well, we will build this model by interpreting types as element of some universe V, which we will construct as a heat in some model of homotopy type theory. And the main part of the proof will be to be able to describe what the quality for this universe V is through an encode-decode argument, and then use that result to prove that it is n-truncated. And in general, we will do this only for n greater or equal to 0, right? So our base case will indeed be assuming that everything supports UIP. So how will this V type look like? Well, the first attempt to do this was with in higher induction recursion, as induction recursion is a natural way to define universes in type theory. And for example, here we see that we are defining mutually a type V and the coding function EL. And the type V contains a code pi bar for pi types, but also a path constructor that tells us that whenever we have two types A and B in our universe V, and their the coding is an n-1 type, and they are equivalent, then A and B themselves are equal. So in this is enough to actually prove that V is univalent. And not only because we can get an equality from an equivalence, but because this is enough to prove the full univalent theorem that says that, for example, one of the forms is that it is contractible, what the thing we see here at the bottom, that the sigma type B in V and equivalences between the elements of B and elements of A, that this sigma type is contractible. And of course, since this is we work in homotopy type theory, this path constructor univ gets decoded to the ambient univalence axiom that we have. Okay, but from here, it turns out that it's actually more convenient to work with an indexed type version of this type V, right? Instead of defining V and L by induction recursion, we can define a type family in V that is indexed by the coding, right? So in V, we'll define codes that are indexed by the coding. So for example, our code for pi types here will be indexed by the ambient pi type, and still will contain proofs for the domain and the codomain. And here we see that this in V doesn't need to be defined mutually with an EL function, because we already have A and B available as arguments of this pi code. Then we can see something about univ, right? So if just mechanically translating the univ for the induction recursion version gives us this type, where we have the codes A bar and B bar for our A and B types. We have an equivalence between A and B, and then finally we say that A bar and B bar are equal over the path given by univalence applied to E. But then we can start simplifying this a bit. Since B and E actually form a contractible pair, because we know by univalence that E becomes an equality, is equivalent to an equality between A and B, then we can cancel these two out. And since being a type of an n-1 type is a proposition anyway, we can also cancel this one out once we don't have B anymore. We are left with this actually simpler type here, which essentially just says that whenever we are dealing with an n-1 type, then its type of codes is propositional, right? For any two codes of A, we have that they are equal. And still we define V as the sigma type of some type, and a proof that it belongs to, that there is a code in V type. And EL now is just the first projection out of this sigma. And just as a notation for convenience, we will write X bar as the second projection whenever X is in V. So now what is left to do is proving that this V is actually n-truncated, because we want to be able to model a theory where types are assumed to be n-truncated, and types will be elements of this V. And to do that, as I anticipated, we first want to kind of give a characterization of what the quality of V is, right? So here we come to it. So equality of V, first of all, we know that V is a sigma type. So its equality is also going to be a pair of equalities. What you have is indeed that the equality in V between X and Y will be an equality in of the types that we can project out of X and Y, right? An equality between element of X and element of Y, and then an equality of the codes, right, between X bar and XY over the previous equalities of the types. What we have to worry about here is mainly two cases. One, which is going to be kind of the simpler case, is the one in which the types being coded are n-1 types. Because in this case, we actually have that the codes are the type of equality of codes is contractible, because Univ tells us that it's propositional and it will be inhabited because we know that they're equal. The other case in which we have to characterize this equality is when they are both codes for pi types, but we don't know a priori that they are n-1 types. Essentially, there are two ways that two pi type codes can be equal. One is if the pi type they code for is an n-1 type. Because since by P we already know that these two types, the two types are equal, then the codes will be equal by the Univ constructor. And the other way is that if these two codes are equal structurally, in the sense that both the domains and the codomain types for these pi types are equal, and the corresponding codes are equal, so S0 equal to S1 and T0 equal to T1, and the quality one gets by combining the equality of the domains and codomain types is the same as the equality P that tells us that the pi types are equal. These two ways can be combined with a join operator, and so the join of these two types will actually correspond in general to equality of pi type codes. Thanks to these observations, we will be able to first define a type family EQ that we then prove equivalent to equality of codes, and then prove that the sigma type of an equality of the types P and an element of EQ at P, that this sigma type is actually an n-1 type. When we combine these two properties, we get that equality in V is an n-1 type. So V itself is an n type. The details of this are in the article, and in the article we also have that the proof is generalized to handle an arbitrary collection of typeformers specified as an indexed container that satisfies a technical condition that somehow ensures that that we can go through the induction to prove that the equality type is an n-1 type. We also are able to generalize this to a hierarchy of universes, V0, V1, etc., where each later universe contains codes for all the previous ones, which means that we can then implement an explicit version of cumulativity as a lift function that lifts any type from VL to VL plus 1. Putting this together, we can finally give a model for partially univalent n-truncated type theory. We start by assuming that we have a category with family that's that models univalence and indexed higher inductive types, which is what we need to be able to model our universe VL in this category. Then we produce a category with family D by modifying the types of C, right? So we use for the category of context of D the same as the category of context of C, but for the types of D we use elements of our universes VL interpreted in C. And then to define the terms, we just use the EL of our universe VL. From this, we can show that D models univalence restricted to n-1 types, and the axiom that every type is n-truncated. That's because we restricted the types in VL to be all n-truncated. So finally, consistency of our theory follows just by picking any category C that can model this universe as VL, and in particular, this could be one of the variants of cubical sets. In conclusion, we know that extensionality for propositions is consistent with uniqueness of identity proofs. In fact, we know something more general, that univalence for n-1 types is consistent with n-truncatedness. The paper also includes a homotopy canonicity proof for an n-truncated cubical type theory with n-1 univalence, which would be kind of a step towards a computational interpretation of this theory. But kind of strict canonicity actually requires more work because we need to provide computational content also for the n-truncatedness axiom, while the computational content for univalence could be kind of inherited from the cubical type theory itself. Thank you for your time.